Okay. Good morning, everybody. Um, let's see. Last time we covered a new way to do integrals. Specifically, we looked at how to use that method to find the indefinite integral of a function. Remember, when I write the indefinite integral, what I'm talking about is just integral of f of x dx. And if we do it, we get some function capital F of x, which is an antiderivative for little f of x, and then we write plus c to say that this whole thing is really a collection of functions. It's the collection of functions of the form capital F of x, and then we add any number we want to it. If we take the derivative of that function, we'll get back little f of x. Okay, so this is what it means to do an indefinite integral. The other thing that we've learned how to do is definite integration. Integral from a to b of f of x dx equals capital F of b minus capital F of a. That was the fundamental theorem of calculus. Okay, so if we do this, we're going to get a number. Okay, so indefinite integration, we get a class of functions. Definite integration results in a number. It's the number that we get when we plug in b and a into f, capital F, and we subtract those two numbers. Okay, so last time we learned, so for U sub, we learned how to do this one, and today we're going to learn how to do definite integration using U-substitution. Okay, and it's more or less going to be the same as usual. We have to be a little bit careful with what numbers we're plugging into what functions. Okay, so before we get into the definite U sub stuff, let's try a warm-up problem. Why don't we try C here as a group, or as an individual. Take about 2 to 3 minutes to try your U sub process here. Remember, what we want to say is that the integral of f of x, f prime of g of x times g prime of x dx is going to be equal to f of g of x plus c. Okay, so sort of the opposite of chain rule here. All right, can I have a show of hands if you're finished with the problem? Those of you who aren't yet finished, do you need a little more time, or are you a bit stuck? Or prefer not to answer? Okay. Well, let's go ahead and try it. Of those of you who said you're done, what do we think we should choose for our U? Let's use this process which I wrote out on the right-hand side. The first thing we want to look for is for some kind of candidate for U. And if we want to find a candidate for U, we should find some function g of x such that we can see g of x and the derivative of that function present in our integrand. Remember, our integrand is just this stuff here. That's our integrand. So we want to look at our integrand and look for a function and its derivative. Is there a function and its derivative present here? What do we think u should be? Emily?
Is it 2x squared minus x plus 7?
Yeah, very good. We should choose u to be 2x squared minus x plus 7. The reason is I can see the derivative of this function present in the numerator. Okay, so that's an indicator that that should be our u. It might be easier sometimes for you to see what should u be if you write these fractions as like 1 over the square root of 2x squared minus x plus 7 times 4x minus 1, like this. Sometimes it's easier to see when you split them up like that. Okay, so I think you're exactly right. This should be our u. So let's let u equal 2x squared minus x plus 7. Now finding du, all we got to do is take g prime of x dx. Okay, so du equals, well, it's going to be the derivative of this thing, 4x plus 1 dx. Okay. The way we did this last time, I'm just using a slightly different method now. So 2 here, I used this method. But I could have just said, okay, du dx, let's compute it. It'd be equal to 4x plus 1. And then we'd move the dx over to the other side and get du equals 4x plus 1 dx. Okay, same process. A little bit streamlined. Okay. So now we have u and du. Let's replace it. Let's write this as an integral using u. First of all, I don't need to adjudicate constants because du looks exactly like my leftovers. Okay? So let's write this as an integral. It'll be the integral of, how can I write this with u? Yeah?
1 over the square root of u.
Very good. 1 over the square root of u du. Okay? If we look at our original function, the square root of u, that's this thing. The square root of u is this thing. And then the du is the leftovers, which are 4x plus 1 dx. Or 4x minus 1, excuse me. Okay, now how do I do this integral? Any rules I can use? I want to find the antiderivative of this function, 1 over the square root of u. Is it the fraction that's bothering you, or the square root, or the combination of the two? Or you guys feel like you have the right answer, but you don't want to be wrong in front of the class and get embarrassed? That's okay. Okay, math is like 99% making mistakes. So making mistakes in class is really seriously going to benefit you in the long term. But I won't force you guys. Let's do it together. I'm going to rewrite it as u to the negative 1/2 power du. And then I'm going to use the power rule. So if I use the power rule, negative 1/2, I add 1 to that, I get u to the 1/2. And now I should divide by the new power. So if I divide this by 1/2, that's the same as multiplying by 2. So I get 2 square root of u plus c. Okay. So last thing I have to do, switch all of this stuff back to x. So the way I'm going to write that is just 2 times the square root. Where I had u before, I'm going to write what u was equal to. It's 2x squared minus x plus 7. And then I'll add c. And one way you can check your work is, if we take the derivative of this thing, we should get our original integrand. Okay. Questions about the warm-up problem? Okay, hopefully I can start to build up your confidence with U-substitution today. So I'm going to add a page in here and talk a little bit about how we do definite integration using, oh geez, I guess I better move this back up to where it was before. There we go. Okay, so we're going to learn how to do definite integrals using U-substitution, and there's kind of two methods. Let me go with blue. method 1 is going to basically be the same as this stuff, so I'm going to copy it in and put it down there. Except we're going to edit it slightly. And we'll do the next one as well. Okay, so method 1 is going to be really similar to doing indefinite integration for the first while. We're going to do the usual, look for the inner function g and its derivative g prime of x, set u equal to g of x, and du equal to g prime of x. And then we're going to adjudicate constants if needed. And then here's where things are going to start to get a little bit different. Down on this step. We're going to need to play a little bit with our limits of integration, 0 and 1 in this case, for this problem. Okay, we have to play a little bit with those. So, method 1 is in fact, I'm just going to delete that. Method 1 is change limits of integration using u equals g of x so that the limits are in terms of u, then solve the integral with u. Okay, that's one method. The other method, I am gonna bring this down a little bit because we'll use that. The other method is make sure to note limits are x equals a and x equals b, and do not plug until we change back to x. So then replace and integrate, switch back to x, and then plug in using x equals a and x equals b. Okay, so this will be easier once I do an example. Okay, but basically the idea is if I look at this integral here, the bounds of integration are the x values 0 and 1 for which I'm integrating. Okay, so I've got 0 and 1. If I then switch this integral to be in terms of u equals g of x, and I plug 0 in for u, I'm going to get the wrong answer because g of x equals 0 doesn't necessarily mean that x is going to be 0. Okay, so u is not going to be 0 typically when x is 0. So we have to be a little bit careful about what we're plugging in. So we have to wait to plug in until we have changed everything back to be in terms of x. Or we can do something clever and use g of x to switch the bounds of integration to be in terms of u. Okay, so let me give you a problem where I'm going to use both methods side by side so that you can see the differences. And in general, sometimes it's going to be faster to use the one, and sometimes it'll be faster to use the other, and I'll talk a little bit about when we should use one versus the other. I'm going to write over this problem so that I have a little bit more space. So, method 1. That's too thick. All right. So, method 1 was change the limits of integration using u equals g of x. Okay, so I've got x times e to the negative x squared. This is a u substitution problem because I have a product of functions here. I don't know how to do the integral of a product of functions. I can find its derivative, but I don't know how to do the integral, so I need to use the only technique that we have for doing integrals, which are more complicated than sort of simple functions. I need to use u-substitution. The first thing I should do is look for what is u and du. So, in doing so, I need to look for something which looks like an inner function, and I need to look for the derivative of that function. The two that are jumping out at me are negative x squared and x. X is not quite the derivative of negative x squared, but it is a constant multiple thereof. So those are going to be my u and my du. So I'm just going to choose u to be the power here. Negative x squared. Okay, and then du is then just going to be negative 2x dx. And now I kind of want this right-hand side here to look like my leftovers, which are going to be x and dx. So I'm going to solve it for that. So I'm going to multiply both sides by negative 1/2. So negative 1/2 du equals x dx. And now I'm ready to replace everything. Okay? Now I'm ready to replace everything. Okay. So I'll have the integral of e to the u times negative 1/2 du. Now, what I need to be careful about is these bounds here, 0 and 1. This integral is now in terms of u, okay? It's now in terms of u. So here's where the two methods differ. For one method, we're just going to write x equals 0 and x equals 1. We'll have negative 1/2 e to the u du. Okay. For the change the bounds method, what we're going to do is we're going to take these two numbers highlighted in blue and plug them in to this function u equals negative x squared. They're x values, so we're going to plug them in for x. Okay, so when x is 0, u is going to be 0, so I'm going to keep 0 here. And when x is equal to 1, u will be equal to negative 1 squared, which is just negative 1. Okay, so here's the difference. On the left-hand side, the bounds of integration are values of u. On the right-hand side, the bounds of integration are values of x. We're going to have a little bit more work to do on the right-hand side because we're going to need to wind up changing this all back to x before we can plug in. Okay, so let's finish this up. We'll have negative 1/2 integral of e to the u is just e to the u, and we're going to evaluate that at 0 and negative 1. And we'll get, when we plug in -1, we'll get -1/2 e to the -1 minus or plus 1/2 e to the 0, which is just 1 minus 1 over 2e. So that was the method where we changed the bounds of integration. Okay, then for this second one, we're going to do the same kind of process. We're going to get -1/2 e to the u, and the way we're going to write it is we're going to write our bar, but we're going to write x equals 0 and x equals 1. Okay, to make sure that we're going to use x. And now what we're going to do is we have a function here being evaluated at some endpoints. However, the endpoints which we're supposed to evaluate are x values, and the function is in terms of u. So the way we can solve this is either by switching the endpoints to look like u's, or by switching the function to look back like x's. So we'll do it the other way this time. We'll switch the function back to its original form by taking this blue thing, u equals -x squared, plug it in for u, we get this is equal to -1/2 e to the -x squared, and now we can plug in these values 0 and 1. Okay, so I dropped the x's for my bounds, because now they agree with the variable which is in the function. Okay? So I get the same thing I got before, -1/2 e to the -1 plus 1/2 e to the 0 equals 1 minus 1 over 2e. Okay, so those are two methods, and basically the way it works is, for one, we've got some integral of some function of x, and then we change this to look like why don't I write it correctly? I'll write integral of f prime of g of x times g prime of x dx. And what do we change this to look like? We change this to look like f prime of u. So this was from a to b. We change it to either look like f prime of u du from g of a to g of b. So u equals g of x. And then this goes to be f of u evaluated at g of a and g of b equals f of g of b minus f of g of a. That's the method where we change the constants. Okay, so or the other method we can take is method 2. We just write integral from x equals a to x equals b of f prime of u du equals f of u, and then we write, these are two different methods, f of u, and then we write evaluated at x equals a, and then x equals b, and then we replace u by g of x again, and we keep x equals a and x equals b. And then we wind up with the same thing, f of g of b minus f of g of a. Okay, So the two methods, it's really just your preference. Do you want to do a little bit of work up front and change the bounds of integration so that you can just finish the integral using u? Or do you want to just leave the bounds as they are, do the u substitution, switch everything back to being in terms of x, and then plug in? Okay, so it's a little bit of like an order difference. Yeah?
I'm a little confused. Which one is method one?
Okay, so method one. So this was method two here, and this is method one, and then on this side, again, it's 1 on the left and 2 on the right, I think. Yeah. This is method two. Okay, so let me draw your attention to this column here with method one in red. The point here is to tell you exactly how to find the new bounds of integration. If we switch the bounds of integration, whatever we pick to be the function of x, which we call u, we just plug our bounds into that function to get the new bounds. Okay, so the new bounds will just be not from a to b, but from g of a to g of b, where u equals g of x. Okay, that's really what's going on there. Whichever method you use is kind of personal preference. I often use method one when it's convenient to plug the bounds into the function g. If g is a really, really complicated function and the bounds are really complicated numbers, sometimes it can be painful to use method one because you have to go and plug nasty numbers into nasty functions, and it's a miserable experience. So there are times where you'd want to use method two over method one. I think most of the time it's more, well, some of the time it's more convenient to use method one. But are there any other questions about this definite integration process using U substitution? All right, I think I've thrown a lot of like methods at you. So what I'll do now is maybe do a couple examples to show you how it works in practice. So, geez, they did not leave me very much space to do this problem, did they? Okay, well, we'll do this problem here, and I will use method one. Yeah, I'll use method one where I'm going to change the bounds of integration. Okay, so I think I should choose u to be the thing on the inside, 2x cubed minus 4x plus 1, because its derivative, or a constant multiple of its derivative, is right out front. It's 7x squared. So if I choose this to be that, then du is going to be equal to 6x minus, oh, hang on a second. Hang on a second, what is happening? Can this be done? I'm not sure this is possible using U-substitution. Two x cubed minus 4x plus 1. We could choose u equals 2x cubed, but then 4x would be like u to the well, if we chose it like this, then we could write it as like the integral of some constant times du times u minus u to the 1/3 times some other constant. I'd want it to be plus 1, and then u to the... No, but that's not going to work. Okay, I think something's wrong with this problem. I'll think about this, and maybe I'll send you guys an email if I find something really clever. But I suspect that this problem was written down in error. Okay, so we're gonna do this problem. Okay, sorry about that. We'll do problem 5 instead. So the total area under f of x equals x over x squared plus 1. This one's a bit more straightforward. What I really need to do is do the integral from -1 to 1 of x over x squared. Oh, you gotta be kidding me. It's one of these problems. I need a simple problem so I can just show you how this works. Here we go. Okay, very sorry about that. This one's a winner, I think. So, to do this problem, we're going to use method 1. We're going to switch our bounds. The first thing I need to do is, as usual, look for u and du. I'm going to choose u to be the thing that's under the square root, and then the derivative of that is nicely out front. So u is going to be equal to x cubed plus 7. And then du is going to be equal to the derivative of that thing, 3x squared dx. Okay. So, x cubed plus 7 is my g of x. If I want to rewrite this using method number 1, what I should do is write down the integral in terms of u. So it's going to be the square root of u times du. And the bounds of integration should now be g of a to g of b. Okay, where a was 4 and b was 9. So now I'm going to write the integral. I'm going to take 4 and plug it into x cubed plus 7. So I get 4 cubed plus 7. And then on the top I'll get 9 cubed plus 7. And then we'll have square root of u du. And now I can just treat this as its own problem. I'm going to forget that x was ever even a part of this problem. So now I'm going to find the antiderivative. It'll be u to the 3/2 divide by 3/2 equals u to the 3/2 2u to the 3/2 over 3. We're going to evaluate that at 4 cubed plus 7, 64, plus 7, 71. That's the lower bound. The upper bound is 9 cubed plus 7. I think it's 729 is what 9 cubed is. Let's check. Yep, 729 plus 7, 736. Okay, and now we're going to finish. We just plug those numbers in. 2 times 736 to the 3/2 power, divide by 3, and we subtract from that, we're going to plug in 71 now. 2 times 71 to the 3/2 power, all over 3. Okay. So that's how we do method number 1. Okay? Notice, once I got to this step right here, once I had everything in terms of u, including the bounds, it was kind of like I was starting a whole new problem. All right? And it's like I imagined that they just asked me this thing instead of the original problem, and that's a problem that I already know how to do, okay? So in calculus, we're always taking problems that we don't know how to do and trying to turn them into problems that we do know how to do. Once we have a problem that we do know how to do, all that's left is just to do it. Okay, that's kind of the spirit of this method. Emily, do you have a question?
Where did you get the 3/2 on the u from?
Great question. So the integral of, was it from 71 to 736 of, I wrote square root of u as u to the 1/2 power du, and then I used the power rule to increase the power by 1. So 1/2 plus 1 equals 3/2. So that became u to the 3/2, and I divided by the new power, which was 3/2. Dividing by 3/2, same as multiplying by 2/3.
Thank you.
Yeah, no problem. Any other questions? Okay. We'll do this next one where we're going to keep the bounds in terms of x. Okay, so I'm going to use, so this was method 1, and now we'll try one using method 2. Okay. So, first thing to do is look for two functions, one of which is the derivative of the other. I think the function we should choose should be this whole thing that's in these parentheses here, 2x squared plus 16. I can see the derivative of that is right on top. So let's try it. Try u equals 2x squared plus 16. Then du will be 4x. Now the top doesn't quite look like du, but it does look like 5 times du. Okay, so here's my u, 2x squared plus 16. That's showing up right here. And my leftovers, highlighted in yellow, 20x dx, are on the right-hand side of this equation. So I'm just going to replace them by the left-hand side, which is 5 du. Okay, so I'll write this as being equal to the integral. I'm going to keep my bounds as x equals 0, and x equals 1. And now I'm going to replace the red stuff by 1 over u to the 4th power. And I'm going to replace the yellow stuff times 5 du. Okay. So, clean it up a little bit. Leave the 5 out front. Integral from x equals 0 to x equals 1 of u to the negative 4th power du equals 5 times u to the negative 3rd power divided by the new power and evaluate at x equals 0 and x equals 1. Now, it would be a grave mistake to try to plug in these numbers now. Okay? Because these values on the right-hand side are x values, not u values. Okay, so we can't plug x values into u values. It's not going to give us the right answer. So what we need to do first is switch the inside back to being in terms of x, and then we can plug x values into x values. So I'll write equals 5. I'm going to pull that -3 out. Right, this says -5/3. And I'll just rewrite the whole thing. X equals 0 and x equals 1. And this is going to be equal to -5/3. And then inside, I'm going to write 1 over 2x squared plus 16 to the power 3, evaluated at x equals 0 and x equals 1. And now I can plug in those values. I'll get -5/3 times, plug in x equals 1, we'll get 1 over 2 plus 16 cubed, 1 over 18 cubed, minus 1 over 16 cubed. Okay, so that's one where we use the second method. So, either method that you want to use is fine. One thing that I'll caution you is that if you choose to use method 1, you must remember to change the bounds of integration. That's the crucial thing that you need to remember for method 1. For method 2, the crucial thing to remember is don't change the bounds, but do change the function back to x before you plug in. Okay, so those are the two methods and the crucial thing to remember for each one. Okay. Let's see, I think we're out of time. So we'll stop here for today. If you want to see this extra problem 2, maybe I'll do it after class. Otherwise, I'll see you next time. I have office hours today from 12 to 1. So if you need some help, go ahead and come. There's new homework due on Friday. And I'll send you guys an email about that problem if I figure out some clever way of doing it. Yep, have a good one.